sampling distributions and the central limit theorem. These things go together. Sampling distributions is actually something that I showed in that pre-video 18. Did you see that one? It's a separate video than this one. It's only like 8 or 9 minutes tops. It's watching me play around with a little applet on this website right here, if you can go and play with it yourself if you like, where I show you what happens when, let's say you have a normal distribution here. I use the weights of kaijus, individual kaijus. Their weights are normally distributed like this. Well, what happens if you go taking samples from those kaijus? You take a sample of 10 or whatever. If you take samples of 10 and then you find the mean of that sample and then you plot those means, you can do it over again, over again. What if you do every possible sample of 10 kaiju? What you'll find is that your sample means, well, they have the same mean, of course. The means line up, right? Those are the means. They line up. They're the same. But for the samples, the standard deviation is going to get skinnier. So a little nomenclature here. If you haven't watched that video, it's worth watching just so you get a feel for what I'm saying here. But let's talk about the nomenclature here. If you have a distribution of just individuals, so like that's what this is, individual kaiju. I think it was weights of individual kaiju. They're normally distributed. They had a mean of, I don't know, I think it was 16 tons, but that's the symbol you use for the mean of the individual kaijus. And then they have a standard deviation, and you use that sigma symbol for the standard deviation. Now, where's the standard deviation on this? It would be just about here, because the standard deviation is the distance from the middle to right here, where it's called the inflection point. We're kind of curving this way, but then we're kind of curving this way, and right in between is called the inflection point. So that distance is what we mean by the standard deviation. So anyway, for the individuals, you got the mu and the sigma, right? Now, when you go taking samples and keep the sample size the same, so samples of size n, right? Well, each sample will have a mean. That's supposed to be an h. Each sample has a mean, and we call the sample mean x bar. We don't even use the mu thing at all. We call it x bar, and each sample has a standard deviation, and we just call it little s, standard deviation of a sample, right? So that's what this is saying. Each sample has a mean of x bar and a standard deviation of s. Okay, but you take every possible sample, and then you graph the means for each of these samples. What you'll find is that the mean of all these samples, of course it comes out the same as the mean of the individuals, but we give that a special symbol, the mean of all of the samples. The mean of all the x bars. Maybe say it that way. The mean of all the x bars comes out to be the same as the mean of all the individuals. They're the same. But again, the key point here is that the sigma is different. You will see, let me erase some of this gook getting in the way here. You will see that, not that you will see, you've already seen that this is skinnier. If you watched this, you already saw it for sure. But anyway, it's skinnier, and so running out of space here. So the standard deviation here, remember you want to go out to the inflection point. It would be somewhere around there. So somewhere here would be the sigma sub x bar, right? It has a skinnier standard deviation. Okay. Now, the standard deviation shrinks. That's what, and the mean is the same. That's what the central limit theorem is telling us. It's just a statement of these two facts. The mean of all the samples is the same as the mean of all the individuals. That's what that says. And the standard deviation of all the sample means is smaller. And it's smaller this way. So this is new. You divide by the square root of n, where n is, of course, the sample size. So you divide by the sample size. So the sigma comes out smaller. That's all this is saying. And it's interesting that it comes out smaller by exactly this factor, divide by the square root of n. So in that pre-18 video, I guess I'll call it, we were able to set the sample size. Oh, by the way, the population we drew from had a mean of 16 and a standard deviation of 5.00. And then we took samples. We didn't do all of these, but I did. We could set the sample size to any of these numbers, right? So when I set the sample size, and I should be making a new table here, sample size n, then we got a standard deviation. When the sample size was 2, the standard deviation wasn't 5 anymore, it was 3.54. When we did a sample size of 5, we got a 2.24 instead of a 5. In other words, this one has a 5, but if I did samples of size 5, it shrinks to this. It shrinks. 10 came out to 1.58. Samples of 16 came out to 1.25. Samples of 20, notice how skinny it's getting. Samples of 25, it came out like this. And the point to note, I didn't do this when I simulated. This is just, these are all simulations is what these are. Okay. Those are the simulations. But just grab any one of these, like this one. Notice that 1.58 is, you take the 5.00, which was the sigma, and you divide it by the square root of 10, which is the sample size. Do that on your calculator, and that's how you get 1.58. So it checks. It checks beautifully. It's wonderful. So again, the main point of the central limit theorem, the means are going to be the same. All the sample means, we'll have them. if you plot the means of all the samples, the mean's going to come out the same as for the individuals, but the standard deviation of all your samples is going to have a smaller standard deviation, and it's going to be skinnier like this. All right, let's show you how this ends up affecting our lives. Okay, here's how this affects your life. So what do we got going on here? Coke cans are labeled 12 ounces. Standard deviation is reported to be 0.11 ounce. Okay, fine. So what you're interested in is, I wonder if they really are 12 ounce. Maybe you work for the Consumer Protection Agency or something. You want to make sure they're really 12 ounce. Remember Subway got sued because their footlongs were less than 12 inches. Uh-oh. So let's see if Coke, the 12 ounce Coke, has 12 ounces or not. So Biff says, I'll do it. And he grabs a can of Coke at random. He weights it. He weighs it. Okay, that's better. He weighs it, and he gets 12.15. Oh, that's actually heavy, so that's good. But the question is it unusually heavy? Because that might be nice to know. Is this unusually high? Well, this is what we used to do a couple lectures ago or so, right? You get a z-score is what you do. You take your x minus your mean over your standard deviation, and we're talking about individual cans. There's nothing different here. There's nothing sample-wise. It's just a sample of one. It's just an individual can. So it weighs 12.15 ounce. The mean is supposed to be 12. That's what they tell us. And the standard deviation is supposed to be 0.11. That's what they tell us. And so if you work that out, you get a z-score of 1.36. And then you have to go to the table and look up the area, right? The area is the probability. So I got the table on the next page. You ready for a scroll? Okay, 1.36. Here's 1.1. No, not 1.1. 1.36. 1.36. Well, here's 1.30. 1, 2, 3, 4, 5, 6. This one. 0.9131. Come back up. Okay, so the area to the left is 0.9131. Now remember the situation we got going on here. We got a z-score of 1.36. Here's a quick review question. How do I know that the 1.36 is over there? How do I know that the 1.36 isn't over here? There's a way to know. Now, of course, we're talking roughly. But remember, z equals 0 is in the middle. Z equals 0 is in the middle. Positive z's are all over here. Negative z's are all over here, right? So that's the first thing to keep in mind. Z equals 0 is right in the middle. The other thing to keep in mind is that the inflection point, where it changes curvature, that's z equals 1, right? So that would be a z equal to 1. That's a 1. And if you go back to this inflection point, that would be a negative 1, right? So the inflection points, it's 0 in the middle, That's a 0. 0 in the middle, and if you go out to the inflection points, that's where your plus and minus 1 is. Okay, cool. Okay, cool. Okay, cool. Okay, cool. So the 1.36 had to be a little bit beyond the inflection point. Yeah, it's about there. So the table tells us that the area to the left is 0.9131. Is that what we're interested in? Well, the question is this unusually high? So unusually high, we're talking about how likely is it to get a can at least this heavy? So at least this heavy would mean basically this heavy or heavier would be the area to the right. So you'd have to go 1 minus the 0.9131, or you get, what's that, like 0.0869. If I make it a percent, it's like an 8.7%. So does that seem unusual? Nah, that's not unusual. Now we have to remember some other stuff. How to define unusual. It all comes together, doesn't it? Math always builds. You've heard that. Builds. So how do we define unusual? Well, we'd have to have a probability less than 0.05 if we're talking, what do you want to call it? Everyday use. For everyday use, we usually use we call this a significance level of 0.05. It means it's a 5% chance that we could, or it's 5% that we could say this is dumb luck that we had something this heavy. Well, this is 8%. That's more than 0.05, so it doesn't even meet that threshold. So let's go like this. That's our everyday one. And remember, we had 0.01. That's kind of like if you're making pills, you want them to be safe. Or 0.001. That's like if you're going to doubt a law of physics or something. I don't know. So anyway, that's that. So it's probably not a heavy Coke. Bonnie is going to try too. Bonnie says, you know what? I'm going to take a sample of 36 Cokes. Now, a simple random sample doesn't mean you go to the store and get 36 Cokes. It probably means you go to Cokes all over the country and grab 36 from random locations all over the country. Anyway, and weighs them. Now, the mean weight of these 36 Cokes, the mean weight of this sample is 12.04, which is very close to 12, right? So it might seem like, that can't be too high. But we should check. We should see what's the actual probability. What is the probability that our sample mean would be 12.04 or heavier, at least that heavy. So it might look okay, but you got to do the math sometimes before you know. So let's do some math. Now, because we're measuring 36 cans at once, actually, remember, central limit theorem says our sigma will shrink. That's important when you're calculating a z-score. You want to use the right sigma when you're calculating a z-score. So what we'll have to use is a sigma of the samples, which is the sigma for the population of individuals, divided by the sample size, square root of sample size, square root of 36. So in other words, we want to use the, what was the sigma again? Got to scroll up. 0.11. We want to use the 0.11 divided by the square root of 36. And if you do that, you're getting like 0.01833. Again, that's the sigma of the samples. So that's going to change our z quite a bit, ain't it? So z, you still do the old x minus mu, but now you're using the different sigma, because the sample that you're, the x that you're using is well, I don't know, the x is to 12.04, that's the same. But the mean that you're using is actually the mean of the samples, but it's always the same as the mean of the individuals. So the mean was 12, right? Okay. But now we're dividing by this much smaller sigma thing. And so 12.04, take away 12, divided by that, you get a 2.18. Ooh, that's a much higher z. We had 1.36, recall. This is 2.18, even though they're just a little bit heavier. Yeah, but all 36 of them, on average, are a little bit heavier. That's saying more than this one can was a little heavy. No, this is 36 cans, and they're all a little heavy. So we got to figure this out. Area left, if you look at the table, for 2.18. Okay, I'm going to go to the table now. 2.18, where is that? There's the 2.1. That would be here, right? So that's 0.9854, I reckon. let's grab that, bring it back up here. 0.9854. Oh, wow. So that means that when our z-score is way up here at 2.18, the area left is 0.9854. So, or heavier, means we want to be on the other side. We don't want the 0.9854. We want to go 1 minus that, which is just about, just call it 1.5%. Is that unusually high? Well, for everyday use, for everyday purposes, remember we use 5% as our rule of thumb. Is this significant or not? It is. It's under 5%. So something might be a little strange here. It's not 1%. It's not like, medical research quality grade, surprising, but it's still 1.5%. So you're thinking, wow, if there's only a 1.5% that this is a dumb luck chance, then, well, if I'm running the Coke assembly lines, I might just turn the dial, just tap it a little bit, try to make them just a little bit lighter, just a little bit, so I don't have to waste money on Coke. Selling more Coke than I think I'm selling or whatever. Okay, so that's the idea. So you look back at this and you say, okay, when we have a can of Coke, individuals, do the z-score in the usual way. When you have a group of Cokes, 36 Cokes, you're going to do the z-score kind of, that part's all the same. The difference is right there. You're going to change the sigma that you use. You're going to use a sigma over square root of n. That's the big deal. Sigma over square root of n is the big deal. So we've got 2 more examples that are actually related. But at the top of this page, sigma over square root of n. That's the big deal. If you're talking about a mean of a group, then you're going to have to take your sigma over square root of n. Central limit theorem. Adult males. One more example, 2 parts. Adult males have a mean weight of 182.9 with a standard deviation of 40.8. Okay. I don't know what year that was, but okay. Find the probability that a randomly selected male weighs more than 156.25. I don't know why we're interested in that particular weight, but we can do this. It's an individual. Do it the old way. Maybe you should do it the old way, just for practice. You can pause and you can come back. So I got the 156.25 is our x of interest, and the 182.9 is the reported mean, and the reported standard deviation is 40.8. That's for individuals. And you work that out, and what do you get? You get, I don't know. You get, notice it's negative, right? Negative 0.65 is our z. And then you go to the table, and if you trust me, I got an area to the left of 0.2578. So what's the situation here? It's always a good idea to kind of draw it out and say, well, the z-score was negative. Negative, remember, 0's here, and at the inflection point is -1, so we're somewhere around here. Negative 0.65 is our z-score. Area left would be, of course, this area, 0.2578. Are we interested in area left or area right? Well, find the probability of random area weighs more than. We're interested in the area to the right. So heavier, I'll just say heavier, is 1 minus 0.2578. Or about, what, 74.2%. So there's like a 74% chance that if you grab a male at random, I assume, no, it says adult male at random, that this guy is going to weigh more than 156.25 pounds. Okay, that's old. Here's new question. A men's dormitory. See, this is like an application now. All right, here's the other part. So, a men's dormitory. It's got an elevator in it. And the elevator is rated at 16 people or 2,500 pounds max. Now, the 16 people is kind of a rule of thumb, really. It's the 2,500 pounds that really matters. And I'm assuming that when they came up with 16 people, they were thinking of both men and women and children and all this other kind of stuff and saying, well, just roughly 16 people. But if the 16 people are all really heavy and they go over the 2,500 pounds, then you got a problem, right? So that 16 is kind of a rule of thumb, but the 2,500 is kind of more important. Now, this being a men's dormitory, and men being heavier than the general population, we might want to check what is the probability that if 16 men get on board, that they will weigh more than 2,500 pounds. That'd be nice to know in a male dormitory. So this is a practical application. So I'm going to rephrase this problem so that it looks like a central limit theorem problem. We have, let's call it a sample of 16 men gets on the elevator. Mean? No, men. I got statistics on my brain here. A sample of 16 men has a mean weight, because that's how the central limit theorem works. We're talking about means of the sample, as a mean weight over, now you take that 2,500 pounds and you divide it by 16, and you say, well, the mean in that case would be, oh, ain't that a coincidence, 156.25 pounds. So in other words, the elevator can hold 16 people who weigh this much, because 16 times this gives you the 2,500 pounds. So as long as the mean weight of people stays under 156.25, the elevator is going to hold. So that 156.25 rings a bell, right? And we're doing that up here? We're doing that up here. So we found in part A that the chance of a male being heavier than that was, well, 74%. I guess that's nothing to sneeze at. What's the chance that the whole elevator, that 16 people in an elevator, 16 men in an elevator, is going to weigh more than this? Is it also 74%? Are we done already? No, it's not, because this is different. This is a group of 16. 16 group of 16. So when you have a group, you have to use, when you're calculating z-scores and stuff, you have to use this standard deviation. You have to use the standard deviation divided by the square root of the sample size. So that would be, use the sigma. What was the sigma? The sigma was 40.8. Okay, use that, but it has to be divided by the square root of your sample size, which will be 16. And when you do that, you get 10.2. So our new z, you use the old, oops, let's do it this way, x minus mu over sigma, but not just sigma, sigma of the samples. And so that's going to be, we're trying to, let's see, 156.25 is what we're interested in. The mean weight of the men was, what was it now? It was 182.9. That goes here. Put the sigma sub x bar underneath here. Now you're getting a z-score of, whoa, negative 2.61. Ooh, that's a low z-score. So think about what this will look like. A z-score of negative 2.61. Again, there's 0, there's negative 1. It's out here. It's way out here. So negative 2.61. The table will tell us the area left, and it's not going to be big. So the area left is, did I look this up? Yeah, I did. 0.0045. Holy cow. So remember, what we're really interested in is the heavier. What's the probability of it being heavier? So this sample of 16, the probability that it's going to be heavier than the 156.25 pounds is 1 minus 0.0045. So that's like 99.55%. Almost every day, if 16 guys from this dorm gets on the elevator, you can bet 99.55% certain that elevator is going to be overloaded. What you might want to do is you might want to say limit 10 or something, if you're like the safety guy or whatever, limit 10 or something. But okay, so this is how this works. Sigma over the square root of the sample size.